All right, good morning, everyone. So I sent out an email, I think last night, that yesterday I had some computer problems. My computer just like completely, I don't know, it disappeared. It wouldn't come back to me, but I got it back. So I'll be doing the solutions to the homeworks today and tomorrow. And so the homeworks that I still haven't done are, I believe it's those two I still need to put out there for you. So today what we're doing is we're going to talk about one-to-one functions, and then we're going to get into 8.1, which is the inverse trig functions. So 6.2 is where we're going to start. This should be a review. This is something you cover in college algebra, but I'm going to be pretty thorough about it. So if you don't remember it, it's okay. You should be all right. Any questions before I begin? Ready? Okay, so we have this concept of what are called one-to-one functions. And this is a lot of just definitions. So this is going to go pretty quick. Just remember, you'll be able to go back and watch this if you need to. So don't worry about like copying everything down here. A one-to-one function, well, you should remember, first of all, what a function is, right? So a function has the property that it has inputs and it has outputs. And to be a function, it says that for every input, it has to go to exactly one output. So this would be a function. You know, two different inputs go to two different outputs. But if you have a third input, let's say, it could also go to the same output. And this would still be a function, because the condition for a function to be a function is that for each input, it goes to one place. And the place it goes to, the number that comes out, it can be the same number as another input. So two inputs can go to the same value. What you cannot have is this. You cannot have one input go to two different outputs. That would be where it fails to be a function. So now what we're doing is we're adding something to this, a new condition, and that's what being one-to-one is. So one-to-one's function means that if you have two different inputs, they will go to two different outputs. You'll never have, when you look at the outputs, you'll never have a line going from two different inputs to an output. Like this right here would fail to be one-to-one, because for this output, there's two inputs that go there. So this would fail to be one-to-one. This would be a function, but it would fail to be one-to-one. Do I need to clarify that? Does that make sense to everyone? What's wrong with this one?
It's got one of the inputs is going to two of the outputs.
Yeah, so that's not a function, right? That's not even a function. So this fails to even be a function, not a function. It says it down here, right? And then this one is a function because each input only goes to one place, but it's not one-to-one because, see, this one comes from two different places. This is the only one that every one input goes to one output. And you can kind of see why they call it one-to-one. Every one input goes to one output, and that's it. Okay, so when you have one-to-one functions, you have something very, very nice when you look at the graph of something like this. So when you look at a graph, okay, so let's just look at this graph right here. Notice that if I plug in x1, it's spitting out this value, whatever this value is, h, right? That's how high the point is. But if I plug in x2, I get the same height, the same output. So if you draw that in a picture, that means x1 goes to h, but then x2 also goes to h. And therefore, this would not be one-to-one. Okay, it's not one-to-one. Now, if you look at this, then if we draw a horizontal line and hit the graph in two places, then that is a quick and easy way to check whether or not a function is one-to-one. So y'all remember to check to see if you have a function, you run the vertical line test. But to check if you have a one-to-one function, you run what's called the horizontal line test. And if you hit the graph more than one place, then it is not one-to-one. So I'll give you an example here. I'll give you a couple examples to look at. So my question here is going to be, first of all, is this a function? So is it a function? And then I'm going to ask, is it one-to-one? All right. So how about this? Let's see. Wrong class. Let me call on somebody here. Didn't get a chance to call on a lot of people last time. Is Quinn here? No Quinn? Quinn? How about Genesis? Is Genesis here? I'm in the right class, yes. No Genesis. Jackson?
Hello.
How's it going, Jackson?
Good.
Okay, so what do you think? Is this a function?
It is a function.
Because it passes the vertical line test, right? Any vertical line you draw, you're not going to hit it more than one time. Okay, so it is a function. Is it a one-to-one function?
It is not.
It is not, because if we draw a horizontal line, well, there are some horizontal lines where we only hit once, okay? But it has to hold for all horizontal lines. So here we actually hit 3 times, and that means it's no, it's not one-to-one, right? Good. All right, how about this one? Let me see. Do a different color here. All right, Jordan. No Jordan. How about Michael Myers? You there? I see you there. Are you there? Samuel?
Yes.
Okay, what do you think? Function?
It's not a function,
Okay,
and
and that's because it fails the vertical line test, right? If I draw a vertical line, I will hit it more than one time.
yes.
So not a function. Okay, good. How about one-to-one?
Yes.
So that's because if you draw horizontal lines, you're never hitting more than once, right?
Mm-hmm.
Okay, now, so I understand your logic. You're wanting to say it's one-to-one, right? But let me go back up to the idea of one-to-one. So let's go up to the definition of one-to-one. Michael, what does it say here? A what? Oh, sorry, Samuel. Sorry. Who was I on? Samuel? I forgot.
Yes.
Samuel. So Samuel, what does this say here? Read it to me.
Which one? The C?
The definition
wait.
of this.
A function is
A
one-to-one
what?
if a function.
A what?
A function.
Okay, a function, right? So you told me right here that this wasn't a function,
Yes.
right? So when it comes to the question of one-to-one, you can't even talk about one-to-one if you're not dealing with a function. So even though this passes the horizontal line test, we will still say it's not one-to-one, not because of the horizontal line test, but because it's not a function. Does that make sense, Samuel?
So since it doesn't even have a function, it doesn't even have.
You
Couldn't
can't even
even
talk about
go
one.
for it.
Okay, not a function. Okay, that's why you can't say it's one-to-one. You can only call a function a one-to-one function. Does that make sense?
Yes.
If it's not a function to begin with, you can't call it one-to-one. Okay, good. So that was that's the most common mistake I see, is people will just do the horizontal line test and forget about the fact that it has to be a function. And I expected that to happen, Samuel, so don't feel bad about it. Okay, what about this one here? This is a graph of a circle. So what do you think, Cameron?
I would say it's not a function.
Yeah, it's not a function, right?
And it's not 1-to-1 because it's not a function.
Yeah, so in this case, as soon as it was not a function, well, then it can't be 1-to-1. So it fails both the vertical, it failed both the vertical and horizontal, right? So, okay, I hope that makes sense. 1-to-1 functions, if you have a function, you can run the horizontal line test, and that's a quick way to check if it's 1-to-1. Now, there's a couple of things that we have that can make quick work of whether or not we have a 1-to-1 function. If you have a function that is increasing on an interval, that means going up as you read it from left to right, like this example. If your function is strictly increasing, so always going up, 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 then what you can say is on this interval, we are 1-to-1. And so just think about it. I mean, we have like vertical line test would always work here, right? And in that little interval, horizontal line test would also work. So on this interval, we'd be 1-to-1. So that's what happens if you have an increasing function. If you're a decreasing function, same thing. You run a vertical line test, you'll be fine. And then if you run a horizontal line test, you'll be fine. So that's all that theorem is saying. Increasing and decreasing portions of our graph are always 1-to-1. Okay, so now we define something called the inverse function, all right? And this is what the next section is about, okay, that we're going to get to today. It's all about this new idea of an inverse function. So I'm going to read this, okay, because, you know, there's a lot here, but I know you can read, but I'm going to read through this. So suppose y is some function of x, okay? So say we have a function, and it is 1-to-1, all right? So let's just say it's 1-to-1. The correspondence from the range of f to the domain of f is called the inverse function of f. The symbol f with this little -1 as an exponent is used to denote the inverse function of f. In other words, if y equals f of x is 1-to-1, then f has an inverse function, f inverse, and then x equals f inverse of y. Okay, what? Okay, so what is that all saying? It's just saying that if we have a function, okay, f, that takes some value x here through the function and spits it out here to a y, that if this is 1-to-1, then we know that y had to have come from x, right? Because it's 1-to-1, it can only come from one place. Therefore, there's got to be some way to take y back to x, some new function that takes y exactly back to x, and that we call the inverse function. We denote it with f with a little -1. All right. So if f, I always think of functions like a car wash. So if f is a function that takes a car in, and you take the car and you put it through the car wash, it comes out as a clean car, the inverse function would be a car wash that you put the clean car into it and it spits it out the other side back as a dirty car. So whatever f does, f inverse undoes it, all right? So it undoes the operation of f. So the big thing here is the idea of the notation here, that little -1 up there, that always denotes the inverse function. Do y'all remember seeing this in college algebra? This shouldn't be brand new to everyone, no? Maybe you did, maybe you didn't, Maddie, no? Okay, so there's something very interesting about the graph of an inverse function, and I think I'm going to do this with an example here. So let's say I have a function, and I'm going to go back to the good old days where you would have x, and let's say I have some function f of x, and I'm not even going to tell you what the function is, okay? But here's what I'm going to tell you it does. It takes the number 1 to 3, takes number 2 to 5, takes number 3 to, let's say, 7. It takes number 4, and let's say it takes it to 8, okay? Then if I asked you to graph this, you would look at these as ordered pairs. 1, 3, 2, 5, right? The x coordinate is the input and the y coordinate is the output. So let me plot these points. 1, let's say this is 3, so here's 1, 3. 2, 5, so 2, and then let's say 4 or 5. And then 3, we're up at 7. And then 4, we're here at 8. Okay, now I don't know exactly what this looks like. It doesn't have to be a straight line. So I'm just gonna kind of like guess that it looks like this, all right? That's kind of what my graph looks like. So let's talk about what the inverse of this graph would look like, the inverse of this function. So first of all, does it look like this has an inverse? What am I really asking you? If I ask you, does this function have an inverse? What am I really asking you?
If it can be like the opposite?
You're asking if if we can make it a one-to-one, correct?
Yeah, I'm really asking you, is it one-to-one? Because when we define an inverse function, when we define inverse, we say, hey, look, if you have a one-to-one function, then it must have an inverse. So if I look at that graph and I say, hey, everyone, does that have an inverse? Then you're just going to say, okay, does it pass the vertical line test? Yes, right? It's a function. Does it pass the horizontal line test? Yes, it does. So it must have an inverse, right? So what would the inverse do? Let's think about what the inverse would do. The inverse would take in some value. I'll just call it x again. And it's going to spit out something. All right. So remember, the inverse function undoes the original function. So if I were to look at the outputs here and list them out, 3, 5, 7, 8. Maddie, where would 3 have to go?
You mean 1?
What's that? I'm sorry.
Did you mean 1? Because you already put 3.
Yeah. Okay. So I'm not Joshua. Okay. So you can answer. Joshua, where would 3 go?
I mean, you're putting 3 on the x, but are you saying you would put our previous value of x1 on the
Yes.
the inverse of f side?
That's right. The inverse. So if the f function takes 1 and spits out 3, so if we'll write it this way, if 1 goes into f and comes out as 3, my question is, where should the inverse function take that 3? Back to where it came from, right? So it's actually more like this should go through the inverse function and go back to 1. So this should be a 1. Right? If f takes 1 to 3, then the inverse function should take 3 back to 1. 3 goes back to 1. So Maddie, where would these go? Maddie? Yeah. I can't hear you. I don't think your mic's working. No, it's okay. You can get it fixed. Brianna?
5 would be 2,
Mm-hmm.
7 would be 3, and 8 would be 4.
Okay, now let's graph these. Okay, let's graph these points on the same axis as this. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I graph the point, let's go with 3, 1. I would go out 3, up 1. 5, 2, so 5, up 2. And then 7, 3, so 6, 7, 3 would be about there. And then 8, 4 would be about here. Now, if I draw these and connect them, I get this picture. Now, it's not a very good picture, okay, because I didn't draw everything to scale. But there's a property here for all graphs of f and its inverse. If you ever have f and its inverse drawn together on the same graph, they will always be, and this is a terrible picture, they will always be a reflection over this diagonal line. Do you see the dotted diagonal line? If you kind of turn your head and look at it, they should be a perfect reflection of one another. Now, that picture sucks, so I'm going to show you a better picture. This is what it should look like. Okay, if you have the graph of f, here's the graph of f right here. whatever f is, if it's 1-to-1, which this blue one is 1-to-1, right? Passes vertical and horizontal line test. Then if you were to graph its inverse, it would be a reflection of the blue one over the diagonal line. That is a very important property of inverse functions, is that there are always reflections over that line y equals x. Any questions there? That will help us graph inverses, and it will help us kind of know what they look like when we see them, because they'll look like a little reflection. All right, so what are some of the properties of a function's inverse? So take a look at, we just talked about this a second ago, but I want you to take a look at this little loop I have here and think about what this is saying. It's saying if you take some value, like let's say you take some number and you plug it into a function, it's going to spit out a number, right? So you take that number, plug it in, let's say this was the number 3, and then you plug it into the function, it's going to spit out whatever f of 3 is. Now, when you take that, if you were to take that answer and plug it back into the inverse, it should take it back here, shouldn't it? To exactly where it came from. And that's what this is saying. This is saying if you plug in x and then you plug it into the f function, and then after you get that answer, you plug that answer into the inverse function, it's going to take it back to x. And that is a property of inverse functions that you have to know. That when you compose the two functions together, f with its inverse, they basically kill each other off. And that's the same thing if you do it the other way. Meaning if you start out on this end, plug in something into the inverse, get an answer, and then plug that back into f, it'll take it back to where it came from. So that's what this equation is saying. All right, I think I would like to show you an example of what this is doing, all right? So a specific example. Let's say that f of x, this is gonna be a very simple example, right? Is 4x. And let's say that the inverse function is 1/4 x. So I'm telling you that that's true. And I'm out of room, so I need to copy this. Okay, so here's what I'd like to show you. Just first visually, let's see what happens. If I were to take, I'm just gonna pick a number here. Let's take a number 3, all right? And let's plug that into f. So what would you get if you plug 3 into f? Let's plug
12.
3 into f. You get what?
12.
12, okay. Now, take that answer and send it through the inverse function. So what would happen if you plug 12 into this? So what happens if you plug that answer 12 into the inverse function?
3.
You would get what?
3.
3. You get back to 3. So see, you start at 3, you go through the f function, then you go through the inverse function, you come back as 3, right back to where you came from. So if I start out with x and go through f, I'll come out as f of x. Then if I take that through the inverse, it'll be f inverse of f of x, but that should just come back out as x. And that last equation is what that property is trying to show you, is that if you take f of x and plug it into the inverse, it spits out the x. All right, now again, because this is kind of a review topic, I'm not going to go too much more into that part of it. What I'd like to do now is do a couple of examples, and the instructions here are to verify that these are inverse functions. So we're looking at two functions here. First one is g is x cubed, and the other one they're telling us is g inverse is the cube root of x. And they're telling us to verify that they're inverses. So the question becomes to you, how in the world do we verify that two functions are inverses of one another? How do we do it, right? So I'm going to tell you how we do it. you must show two things. One, you have to show that f inverse together with f of x will spit out x. The second thing you have to do is show that f with f inverse inside of it will also spit out x. So basically what we're doing is we're trying to show, I'll put this back up here. We're trying to verify two functions are inverses. We have to show that this is true. We have to show that both of these things are true. That's what I'm going to try and do now. Where'd it go? Where'd it go? Okay. All right, you ready? Now, on the first one, they're calling it g. Okay, I see how they're calling the function g and then g inverse. So for us in this problem, we should probably use g, just so we don't use the wrong letter there. So we need to show that, and then we need to show this. So let's do this first one. The first one is saying I take g inverse, and inside of it I do g. So what is Karen? What's g of x?
What's g of x? I'm
Mm-hmm.
not sure I understand what you're looking for. Oh, for this one?
Yep, for part A. What's g of x?
X cubed.
X cubed. So I'm just going to replace that with x cubed. Okay, good, Karen. Now, what are we supposed to do with x cubed? Plug it into the inverse function, right?
Correct.
And the inverse function is this one, right?
Mm-hmm.
So all we're going to do is we're going to write this down, but we're going to, instead of putting x here, what are we going to put? What are we plugging in? X cubed, right? So this is equal to the cube root of x cubed. But Karen, what is the cube root of x cubed?
X.
X, okay? And that is what we were trying to show, isn't it? We were trying to show that when you put g inverse together with g, it will spit out x. And in fact, it does. Karen, does that make sense?
Yeah, it does.
Okay, now we're not done, Karen. We actually have to show that it works the other way around too. We have to show that when we change the order, we still get x. And I'm going to have Anna Marie do that for us. So Anna Marie, you good?
Yes, sir.
Okay, so I'm going to start out by I want to show that this is true, right? So I'm going to start by writing g. Tell me what to put in here. What are we
The
putting
cube root
in?
of x.
I'm sorry?
The cube root of x.
The cube root of x. So we're replacing that with what it is, which is the cube root of x. And now we're supposed to take the cube root of x and plug it into g. So what does g do?
It cubes it.
It cubes it, right? So it's going to take the cube root of x and cube it. And what happens when you take the cube root of x and cube it, Anne-Marie?
It just equal to x.
It just equals x, which we put check. So therefore it works. And that showing both of those things equal x is what you need to show to say that two things are inverses of one another. Okay, now the next one, I'm going to give you a couple of minutes, maybe like 3 minutes, to see if you can do the same thing for these two functions. Show that they're inverses of one another. So show that f inverse of f of x is equal to x, and then the other thing you have to show is that f of f inverse of x is equal to x. Okay, take about 3 minutes, see how far you get with that. Okay, how did it go? Any questions, any issues?
Yes, I do have a question real quick.
Mhm.
Okay, so there's parentheses around x minus 3.
Uh-huh.
So it means the half is half of x minus 3. But wouldn't it just be half x minus 3? Because you're only multiplying the 2 by the x. You're not multiplying the 2 by the 3.
Yeah, so let's work it out. You have a great question. That's what I think can be confusing about this problem is how you work the parentheses. So on the first one, what we do is we write f inverse, and inside of it, what we're going to do is we're going to replace f of x. Caroline, you're going to replace f of x with what?
The 2x plus 3.
2x plus 3. Good. Now, what you're supposed to do now is take 2x plus 3 and plug it into the inverse function. So you're supposed to replace that x with 2x plus 3, which means you replace that x with 2x plus 3, right? Okay, so Caroline, tell me what would happen. If we plug that in, we would start with the 1/2, right? So I'd write down 1/2. And then in parentheses, I'm going to have this, right? X, but it's not x for us. It's actually 2x plus 3, right? So I put that there. But then we still have to subtract 3. You with me, Caroline?
Yeah, and that stays in the parentheses.
Yep, and that's in that parentheses, right? Okay, now do you see that the 3's just cancel?
Yes.
And now you're left with just half of 2x. And then the half and the 2 cancel, you just get x. So we're halfway there. Does that make sense to everyone? Okay, now we have to show the other way. So on the other one, I go f here, and then let's see, is Isa here? Isa, I don't see Isa. Leslie? Leslie, are you there?
I'm
No?
here.
Okay. So Leslie, what goes inside this parentheses here? We're replacing this whole thing, right? I'm sorry? What is the inverse function?
So would it be the whole half?
Yep. Okay, so half of x minus 3, right? So now what we're supposed to do, Leslie, is take that entire expression and plug it into the f function, right? Which means that I'm going to replace that x with everything here in blue, which means I replace that x with everything in blue, right? So Leslie, I'll start with the 2, right? I'll write down 2. And then times what, Leslie?
Half x minus
Half of x minus 3. Okay, that's this. And then what do I still have?
plus 3.
Plus 3 out here. Good. Okay, that all makes sense, Leslie?
Slowly but surely.
Okay. Now, do y'all see what happens with these 2's and the 2.5? They're gone, right? And then you have x minus 3, and then you still have the plus 3 out there. You don't need the parentheses around the x minus 3 anymore because these went away. This just became a 1. So it's just x minus 3 plus 3, and that is equal to x. And that verifies that that works. We good?
Yeah.
Do
yes,
y'all
sir.
remember doing this in algebra?
A little bit.
A little bit?
Yeah, I remember.
Yeah. So here's what I want to point something out to you, that in the problems we're doing, we have a function, right? And it's actually a function that we've seen before, 2x plus 3, that's just a line, right? And the inverse function is another function. In this case, that's also a line. But notice that we have nice equations for both the function and the inverse. We have equations for them, right? You're going to see when we get into the next section with trig stuff, it's not going to be this nice. So we're kind of we're kind of in a unique situation here, but it's going to change. Okay, what about this one? This one's harder. Same problem. Verify that these are inverse functions. So I'm going to work through this one. First thing, let me go and try and figure out. First of all, let me start with this one. F inverse inside of that f of x. And I want this to be x, right? This is what we want. That's the first thing. The second thing I want is to show that f and then f inverse of x is also equal to x. All right, so I'll start with the first one over here. Let's see what happens. All right, I do f inverse. Now, f of x is what I'm going to replace in here, right? And f of x is 1 over x minus 1. Now, I want you to pay attention to something here. Do y'all see that this function f has a domain restriction? In other words, there is a number I can't plug into this. Can someone tell me what number you can't plug in?
1.
Can't plug 1 in, right? Because you'll have division by 0, won't you? So I'm just going to remember that x can't be 1. If x is 1, this thing is broken, right? It's a broken function. So I'm going to continue. Now I'm going to take that answer, this thing right here, and I'm going to plug it into the inverse function. So I have to replace that x right there with that weird expression. So now it's going to look like this. I'm about to write this down. It's 1 over, but instead of x, it's all of that, 1 over x minus 1. So that's this, and then the whole thing plus 1. And what I'm hoping is that this turns out to be x, right? Does it? Well, if you have 1 over a fraction, can't you just flip the fraction over, the one on the bottom? So that just turns into x minus 1 over 1 plus 1. So what I'm saying is if you have like 1 over 2/3, this is the same as 3/2. Anytime you have 1 over a fraction, just flips over. So 1 over this fraction just flips it over. And then anything over 1 is itself. And then that's just x minus 1 plus 1, that's x. And so that would be true if x is not equal to 1, right? So this would be true, right? We would get this to check off. That would all be good, so long as x isn't 1. If x is 1, then we can't do it, right? So it asks here, for what values of x is f inverse of f of x equal to x? That's what we just did. So for what values of x is it true? Well, everything except 1. For every value except 1, this would be true. Questions there? Let's do the other one. The other one, we're trying to check this. We're seeing is f inverse of x. What is that equal to? Okay, so we replace the f inverse with what it is. The f inverse function's up here, so it's 1 over x plus 1. Do we have a domain restriction here? What can't
Yes, it can't be 0.
can't be 0. So let's just remember that, okay? X can't be 0, but let's proceed. We're now going to take that and plug it into the f function for that x. This is going to look weird. We're going to have 1 over, and then instead of x, it's all of that. So 1 over x plus 1, that's this part, and then minus 1. And then these ones cancel, which is nice. So we just get 1 over x. And when you have 1 over a fraction, it flips over. This becomes x over 1, which is just x, and that checks, so long as x is not 0. So just for fun, I think I'm going to graph those just so you can see them. Okay, let me see here. I'm going to graph 1 over x minus 1. And then I'm going to graph 1 over x plus 1. There we go. And you know what? I'm going to graph y equals x. That's the diagonal. Okay, can you all see that the red one is 1 over x minus 1? It is a, do you all agree that this function, the red one, is a function and it has an inverse because it passes both vertical and horizontal line test? Right? And so you can see that the blue one, which is the other function, is its inverse because they're reflections of one another. Right? If you were to take this point and reflect it over, you would get this one. If you take that one, reflect it over, you get that one. And that works for the entire, both graphs. You get this perfect reflection. Now, we said that there were some issues with x couldn't be 0, right? So if x is 0, you have a problem. So you can see that here, you have vertical asymptotes. All right, let's move on. So if you're given two functions, do you all agree that at this point, if you're given two functions, you can check to see if they're inverses, right? You have to just run this test and make sure both of those are true. Yeah, so yeah, let's recap this. Given the graph of f, you can tell if it has an inverse. Right? Do you agree with that? If I give you a graph of something, you should be able to tell me if it has an inverse. And you're just going to run the vertical and horizontal line test, right? And then you're good. Okay. Now, if you're given two functions, you can also tell if they are inverses. And the way you do that is what we just did, right? You take them, you plug one into the other one, you hope that it spits out x, and then you reverse it and plug in, and then you hope it spits out x, right? So that we just did. So if I give you a graph, you should be able to tell me if it has an inverse. If I give you two functions, you should be able to tell me whether or not they are inverses. But here's the real question. Given a function, can you find its inverse? See, because a lot of times we're working with functions and then we're saying to ourselves, well, wait a minute, does it have an inverse? Can I find it? It's different if I give you two functions and say, are they inverses? I've given you a lot of information. I want to be able to just give you a single function and then tell you to go find the inverse. And that seems like it would be a challenge, but it actually isn't. Well, it is challenging, but it's not impossible. So that's what we're about to do here. There is a procedure for doing this. And I'm going to put a star next to this because this actually doesn't leave, even in calculus, we have to find inverse of functions. And in calculus, we don't talk about this procedure. You just assume that the student knows how to do it. So you will see this later. So anytime you have a function and you're asked to find the inverse, here's what you do. All right, so here's our function. What you do is, let me write it down first. Okay, so the first step is we're going to, well, this doesn't, I don't really even like these steps. First thing that we do is we replace this f of x with y. And that's because the output of this function is always the y coordinate, right? The input's x, the output's y. So I'm just going to replace this f of x with y. Now you do something extremely strange. Everywhere you see a y, you now put an x, and everywhere you see an x, you now put a y. So you're going to switch the positions of the X and Y variables. And the reason we're doing this is because whenever you have an inverse, if X, X gets taken over to Y, right, by the function, and then Y goes back to X, right, by the inverse. So X and Y basically switch places. So that's what we're going to do. We're going to make them switch places. We're going to go X is here now, 2Y plus 1, and then Y minus 1. Okay, so we now switch the X and Y. So switch X and Y. And then the last step is to solve for Y. That's the last step here. We need to solve for Y here. So we got to take this equation and solve it for Y. That means get Y by itself on one side of the equation. So watch what I'm going to do. I'm going to take this equation here. First thing I'm going to do to solve for Y is I'm going to clear the fractions. So I'm going to multiply the right-hand side by Y plus 1, multiply the left-hand side by Y minus 1, not plus 1. And what that does is it clears it out on the right-hand side, so you no longer have a fraction. Now on the left-hand side, you have to distribute the X through. Is that clear to everyone? Any questions? Next thing I'm going to do to solve for Y is I'm going to get all my Y's on one side of the equation, everything that does not have Y to the other side. So I'm going to write it down first, then we can discuss what I did. So I moved this 2Y to the other side, which made it minus 2Y. So technically what I did is I subtracted 2Y on both sides, right? And then I got rid of the X on the left-hand side by adding X here and then adding X to the right side. And when you do that, these cancel, those cancel, and you'll be left with the X times Y and then minus 2Y. And then here you'll have your X plus 1. Why do you think I did that step? Why do you think I got all my Y's on one side and everything without Y on the other? Does anyone know why I'm doing this?
Because you could factor out a Y now.
Yeah, because now everything on the left-hand side has a Y. So we can factor it. Pull the Y out of both of those, you'll be left with X minus 2. And now that you have this, and this is multiplication, right? Y times this, you can now divide both sides by X minus 2. And they'll cancel here and you'll get Y equals X plus 1 over X minus 2. And this right here is your answer, but we have to write it a different way. We have to write F inverse of X equals X plus 1 over X minus 2. There it is. I'm going to move this back up here, or you know what, I'll do this. That was the original function, right? Right there. This is the original function, and this is its inverse, right? We think it is. Now, could we check that this is the inverse? How could I verify that we got the right answer?
You plug in the inverse X plus 1 over X minus 2 into the f of X.
Yeah, I could basically do what we did. Where is it? I could do what we did here. See, now we have two functions. We think they're inverses. We could check them, right, to see if they are by putting them together and seeing if it spits out X. Now, I'm not going to do that, okay, just to save us time. But here's what I will do. I'm just going to pick a number just to see if it works. I'm going to pick a number and plug it into this function. So what is f of 2? Let's just plug in 2. Okay, if I plug 2 into f, I get 2 times 2 is 4, plus 1 is 5, so I get 5 on top. On the bottom, if I plug in 2, 2 minus 1 would give me 1, so I get 5. Right? So if I plug 2 into f, it spits out 5. Now, what should happen if I take that 5 and plug it into the inverse function? If I take that 5 and plug it into this, what should it spit out?
2.
2. It should come back and take that 5 back to 2. Let's check and see if it does. So plug 5 into this. Get 5 plus 1, that's 6 over 5 minus 2 is 3. And sure enough, that's 2. And that's not a coincidence. That's because it is correct. So the general steps for doing this, if you're given a function, is to, replace f of x with y, switch the x and y, solve for y. Whatever that answer is your inverse function. How are y'all doing? Again, this is review. I know in college algebra we cover this. Okay, so take a look at this one. Find the inverse of y equals f of x equals x squared if x is greater than or equal to 0. So let's take a look at the graph real quick. Everyone here knows what x squared looks like, right? So x squared does look like this, right? But that doesn't have an inverse. Does everyone agree that doesn't have an inverse? Because it fails the horizontal line test. But they're telling us to look at this function for only x greater than or equal to 0. And that's important because what they're telling us is cut off the left-hand side and only look at this graph when x is bigger than or equal to 0. Very important. They're restricting the domain. When they're giving us the original function x squared, they say, hey, look, only look to the right of 0. Because when you look only to the right of 0, you actually do have an inverse. You should have an inverse there because it's 1-to-1. So now we're supposed to find it. So I'm going to follow the same procedure. I have y equals x squared. Now I'm going to switch the position. So I'm going to say this is x now. This is y squared. And now I solve for y. So here's where I switched. And now I'm going to solve for y. How would I solve for y here? I almost have it, don't I?
Take the square root of both sides.
I have to take square root, right, on both sides. Now, anytime that you take the square root on both sides of an equation, what do you have to do?
Put the plus or minus.
Plus or minus, good. Okay, so what we're saying here is that when we take the square root here and take square root here, we're gonna have plus or minus here, and then this on the right side becomes y, and on the left side becomes plus or minus square root of x. Now, we have a problem. The problem is that this is 2 answers, right? There's 2 answers right now. We have to figure out which one it is.
The plus,
Why the plus?
because x has to be greater than 0. So if you put the negative, it's less than 0.
Okay, yeah, it actually has to do with the fact that look at this graph. Both the inputs and the outputs are always positive, right? And so no matter what, the inverse is going to have to be positive numbers, always. So I'm going to dump the negative and just say square root of x is y. And now this is our inverse function. Our inverse function should be the square root of x. Maddie, to answer your question, you do not have, when you do square root on both sides, you do not have to do plus or minus on both sides. Doing it on one side is sufficient because let me do it with a better example. Let's say I have x. What if I told you x squared was 4? Okay, let's just forget that problem up there. If you wanted to know what x was, you would take the square root on both sides, right? So square root of x squared equals plus or minus the square root of 4. That's what I'm telling you to do. Only do it on one side. The left side is x, the right side is plus or minus 2. Do you agree, Maddie? Okay, now what would have changed had I done it the way that you're saying? What if I do plus or minus x squared, square root plus or minus square root of x squared equals plus or minus square root of 4. Let's just say we did it this way. We would have plus or minus x equals plus or minus 2. All right, let's look at all the different possibilities this could be. Let's say if they're both plus, then it's x equals 2. If this is minus and that's plus, then it would be minus x equals 2. If we do, let's say plus here, but minus here, that would be that. And then I could do minus here and then do minus there. I think that's all the possibilities. And they all, the answers I would get are x is 2. This one would give me x is negative 2. This one would give me x is negative 2. And this one would give me x is 2. Do you follow that, Maddie? So we get the same two answers, 2 and negative 2, which is the same as this. So you're just really creating more work and you're not going to get any more solutions. You're just going to get the same two solutions you would get here. Good question. Okay, so the main point of this problem was that if you start with something that like x squared that generally would not have been a one-to-one function, if you restrict the domain, then it is possible to actually come up with an inverse, so long as you restrict the domain in a way that what's left is one-to-one. Y'all see that? You have to restrict the domain though, and that's going to become critical for where we're headed here. Okay, that's it. That's it for that section. We're ready to get into why, why did we talk about all of that? Well, because now we're ready to talk about the inverse sine, cosine, and tangent functions. So pretty much at this point, everybody in this class should realize that there are 6 trigonometric functions, right? We've studied y equals sine x. We all know that, what that looks like. We know how to graph it. We know how to figure out the period, the phase shift, amplitude, vertical and vertical shifts. We should be pretty comfortable with what that is. We also have cosine x. We also have tangent x. We should know the graphs of all of those. And then we have all their reciprocals. We have cosecant x, secant x, and cotangent x. And we should be somewhat comfortable with the graphs of all of those, right? So the question now becomes, do these have inverses? Okay, these are all functions. Do they have inverses? So we're going to start with just the very first one, and let's just talk about sine by itself. Okay, so I'll call it f of x. Does f of x equal sine x have an inverse? So let me see. Allison, I don't think I've called on Allison.
I'm
Is
here.
Allison, did I call on you?
No,
Okay, how are you doing, Allison?
I'm doing good. How are you?
I'm good. I'm good. Well, actually, I'm a little stressed out right now.
Why?
But, my wife wants to sell our house and move, and I'm just stressed. She's stressing me out.
Oh, that sucks.
Yeah.
Sorry.
No, it's all right. It's all right. It's a lot to have to deal with. But anyway, there are bigger problems that we could have. So, all right. What do you think, Allison? Does sine x have an inverse? What do you think?
It's a function, so yeah.
Okay, it's a function. If we were to draw it, right? If we were to draw the sine function,
Yeah.
then it would do something like this, right? And then it keeps going, doesn't it?
Yes.
So would you agree that, well, it is a function, right? We know that. Does it
Yes.
have an inverse, Allison?
Yeah.
Think about vertical line test, right?
Yeah.
Vertical line test would work for function, but what about horizontal line test? If I draw a horizontal line, am I going to hit the graph in more than one place?
Yes.
Yes, right? So if I draw a horizontal line like this, I'm actually going to hit it like infinitely many places, right? Because this goes forever in both directions.
Mm-hmm.
So if I'm hitting it, then it won't have an inverse. Do you agree?
Oh, no.
Yes?
Wait. Yes. Yes.
Yes, that it won't, right?
Yeah.
Okay. Is everyone clear on this? The sine function is a function, passes the vertical line test, but it fails the horizontal line test. So it is not a one-to-one function. But we still would like to see if we can somehow come up with an inverse. And just like the previous problem that I showed you with the parabola, in general, a parabola will not have an inverse because it will fail the horizontal line test. But if we restrict the domain, then we can look at one piece of it, and one piece of it would have an inverse, wouldn't it? And that's exactly what we're going to need to do if there's going to be any hope of us defining an inverse function for sine. We're going to have to restrict the domain. So generally, in general, it's not one-to-one. Okay, in general, this is not a one-to-one function unless we restrict domain. Does anyone have a question as to what I'm talking about, or why we would need to restrict domain? Is it clear that we would have to do something to avoid the horizontal line test failing? Everyone's okay with that? So the question then becomes, where do we restrict it? How do we restrict it, right? So that we don't get horizontal line hitting more than once. And I have a separate set of notes here. This is actually straight out of my Cal 2 class. These are the notes that I give them when we start off, because when we start off in Cal 2, the first thing we do is we go back to trigonometric inverse trig functions, and then we talk about something called their derivatives. So the first thing I do when we do this is I remind them of what one-to-one functions are, and then I remind them what the trig functions are, and then I say, okay, how do we restrict the sine function so that it does have an inverse? So take a look at this. Here's the sine function. I didn't draw like in every direction in both directions forever, but this right here, just that little segment of it is definitely not one-to-one, right? So here's one thing I could do. I could restrict it there. Can you all see that in black? Do you all agree that just on this little black piece right here, we would be one-to-one?
Yes.
And so I should have an inverse here. If I just get rid of everything else except the black, that would be fine. I could also have done this little green part right there would be fine, right? I'd be one-to-one there also. Or I could maybe do this, that blue part right here, that would be one-to-one. And I could do this anywhere I want on the graph, right? I just need to find myself a nice little chunk that goes all the way from the bottom to the top, but never has a failure of the horizontal line test. And so do you all agree that there's kind of like an infinite number of choices we have here of where we can find that chunk? Well, because there's an infinite number of choices, we, meaning human beings, all had to agree on which chunk we're going to look at. That way that when we talk about inverse functions, we're all talking about the same piece. And the one that we agreed upon is the blue one. That blue piece is what we have all agreed as humans on this planet to be the piece of the sine function we will use when we want to talk about an inverse function for sine. All right, now notice where it goes. It starts out here, negative pi over 2. Okay, whoa, okay. What happened? Oh, shit. My computer, I'm telling you, I've been having issues. Are y'all still there?
Yes, the screen.
Yes, sir.
I can
Hey.
still hear and see you.
What's that?
I can still hear you and see you.
Can you see my screen, or you just see a black screen?
No, it's all
Yeah, I
black.
think the program crashed.
Yeah, I think it did. I'm gonna see if I can't. Yeah, but this is what happened yesterday, and I had like no mouse control over anything. No, no. Let me try Control Alt Delete. Oh, wrong one. I think it's that oh shit.
We can see it again.
Yeah, we can see the screen.
Okay, yeah, something happened and we can't write the notebook cache. Right? Serious disk error. Okay, so I have no idea what happened there. We're all back though, right? You can see my screen?
Yes.
Yeah.
Yes.
All right, let me see. I think my notebook is dead. I can't write on anything, I don't think. Yeah, let me try and close this program. Technology is awesome, isn't it? Okay, that might have done it. I think for the most part, technology has been working pretty good for me until yesterday. I mean, I can do this, but I can't write on it. I can't do anything. So I think what would be most efficient at this time is if I just restart. We still have 30 minutes, so maybe it'll take me about 5 minutes to restart, and maybe we just come back in 5 minutes and see what happens. What do y'all say?
Okay, so you want us to rejoin the Zoom link in 5
Yeah,
minutes?
just try and rejoin. Well, yesterday I couldn't even restart my computer. See, like I can't even restart. So I just have to like power it down.
Okay.
Yeah. So just check back in about 5 to 7 minutes. Hopefully I'll be back up and running. Yeah.
Okay.
Yeah.
All right. Adios.
Sorry.
hopefully that fixed things.
Yeah, I don't know, my computer, when I restarted, did a disk scan. It's corrupted when it must create new cache lock, and you may delete the cache or keep copying, technically make copy. So I think it's something with OneNote. I'm not sure what though. Whoa. What? This would be tragic. Oh, okay, give me a moment. Oh my gosh. Oh, wrong one. What? Sorry, everyone. Let me try something. It's really weird because it seems like I'm logged in. Let me try this one. It's like I've lost everything.
If you remember what your email is, you might need to just try resetting your password.
I think I'm gonna have to. But see. Christ. Okay, so I guess what I'm gonna have to do, just 'cause, I mean, it looks like I can draw on the screen right now. My pen. Okay, I lost, I'm gonna have to somehow figure out where all the hell my notes went, but we should be able to at least proceed for the next 20 minutes. All right, as we were saying, or as I was saying, the idea here is that we have this function f of x is sine x, right? And what we're trying to do is restrict it in a way that we have a one-to-one function. So the restriction that we're going to make is the one that we all agreed upon, which is this one right here. This is where I was trying to draw on the screen. So now I'm afraid to open this, but I was using this earlier. So let me try it. Okay. So what we're doing is we're restricting it just between negative pi over 2 and pi over 2. If we just look at that little segment, then we have the one-to-one that we need. So what we're saying is take f of x is sine x and restrict x between negative pi over 2 and pi over 2. Then sine x is 1-to-1, which means it has an inverse. So the question becomes, what is its inverse, right? What is the inverse function? And, you know, when we were doing the problems before, what we did is we, if I gave you a function, if I said find the inverse, you would write y equals the function, right? And then you would switch the place of x and y, you put x here and you put y here, and then you'd solve for y, right? So you switch them. And then at this point you solve for y. But this is where we run into the major problem, because there is no algebra that we can do to get y by itself here, right? Sine is not like, this isn't multiplication. We can't divide by sin here. That makes no sense at all, because what's sin, right? You can't do that. So we don't know how to do this next step. Do y'all see that? There's no like algebra to get y by itself. So this is where things get really weird. We are just going to define the inverse sine function like this. Define the inverse sine function. We write sine with a little -1 of x. Okay, define it to be y. Okay, so the inverse sine of x equals y. What it means is this, that when you take sine of y, you get x. Okay, I know this is really strange the first time you ever see this, but let me work through a couple of examples and you'll understand what I mean, hopefully. All right, so, I want to leave that there. Okay, so as an example, if I ask you this, if I write this down, what is sine inverse of 1? Okay, so sine inverse of 1, like, what does this mean? All right, that's what we need to figure out right now. Like, what in the world does this mean? It means that when we look at the graph of the sine function, we're trying to figure out where the output was 1 and what angle that came from. Okay, so what angle do you plug into the sine function so that it spits out 1? So what is the angle?
90 degrees.
90 degrees or pi over 2. This should be equal to pi over 2. So another way of looking at this is to say sine of what angle equals 1, question mark, and the answer is pi over 2. Let me give you another one. What is the inverse sine of 1/2? Right? So what this is asking you is sine of what angle equals 1/2? Someone want to tell me?
Would that be pi over 4?
Pi over 4? So how are you getting pi over 4? What do you?
I divided I just divided pi over 2 in half.
Think about the unit circle, right? Think about the common angles. Sine is which coordinate, X or Y?
Y.
It's the Y coordinate, right?
It'd be pi over 6, right?
Yeah, so this is saying at what angle is your Y coordinate 1/2?
Oh, I see.
That good. That happens here, right? This is where your Y coordinate is 1/2. And that angle is pi over 6. Remember how I said you need to learn this unit circle because it's like going to never go away. It's going to continue to haunt you. This is especially here. You have to know these angles or you can't do these problems. Let's do another one. What's the inverse sine of square root of 2 over 2? Now, Joshua, were you the one who answered a second ago?
Yes, sir. That would be pi over 4.
That's pi over 4 because this is saying sine of what angle is equal to root 2 over 2. And so you need to know that that angle would have been pi over 4. Is this making sense, everyone?
Yes, sir.
So far? Okay, how about this? I'm going to try and trick you. What's arc sine of 2 or inverse sine of 2? I said arc sine, excuse me, we haven't even talked about that yet. What is the inverse sine of 2? So that's saying sine of what angle is 2? What do you think? So where on your unit circle is your Y coordinate 2? Is it ever 2? It's never 2, is it? Right? It's never 2. And if you think about it, what you're asking is, when is the output of this sine curve 2? But the normal sine curve is bounded between -1 and 1, right? So there's no way that you're ever going to get 2. So this right here is basically undefined. It's impossible, all right? It's impossible for you to ask what is sine inverse of 2. Let's do some more. What's inverse sine of 0? So this is really saying sine of what angle is 0? So where on your unit circle?
There's 2
Is-
places, right?
Okay, there's 2 places. Good. I'm glad you said that. What are those 2 places?
0 and
0 degrees,
pi.
which is right here. This is the point 1, 0. So there, the Y coordinate is 0. But you also said where?
And pi.
Over here at pi, right? This is also -1, 0. So the Y coordinate is 0. Okay, so our answer could be 0 or pi, right? Or 2 pi. Isn't pointed to the right also 2 pi? So you can't have like 3 different answers. There's only one. And this has to do with our domain restriction. This is why we restrict the domain. We are only allowed to look between -pi over 2 and pi over 2. Or if you like, -90 degrees and +90 degrees. So do you all see that this can't be an answer? Because this is 180 degrees, right? In fact, because of the domain restriction, right? Because of the domain restriction, we are actually not allowed to look anywhere in the second or third quadrants at all, right? Your answers can only come from the first quadrant or the fourth quadrant. And so our answer must be here, what? What angle?
0.
0. It can't be 2 pi. Why can't it be 2 pi? 2 pi means that you go all the way around into here, which means you've gone through the second and third quadrants. Your angle is bigger than 90 degrees. You can't do that. So the only answer it could be would be 0. Are there questions? This is where things start to get a little weird. Here's another one. what is arc sine, or I keep on saying arc sine, I'm sorry. What is the inverse sine of negative root 2 over 2? So this is really asking sine of what angle gives you negative root 2 over 2. So what do y'all think? Where is that on our unit circle?
Be negative pi over 4.
Yeah, so we're over here, down here, right? This is where the y coordinate is negative root 2 over 2. Now that angle, you could say it goes all the way around in here, but you're not allowed to do that because you're not allowed to go past 90 degrees straight up, which means the only way you can do it is to go backwards this way, which means you're going to have a negative angle. And that negative angle, I heard someone say negative pi over 4. Is that what I heard? Or you could say negative 45 degrees, but I'm going to put negative pi over 4. And again, that goes back to this picture. If we're trying to figure out where the y value is negative, the y value here is negative root 2 over 2, the angle has to be somewhere in here because we get negative values here as the output. So it's going to correspond to some negative value between 0 and negative pi over 2, which in this case is negative pi over 4. Let's do another one. So here, we're saying sine of what angle is negative 1/2. So where is the y coordinate negative 1/2? So you got to know this. You've got to know these points here.
Negative 30.
Negative 30. So this is negative 1/2 right there. And that's negative 30 degrees or negative, I'm going to say, I'm going to stick to radians, negative pi over 6. What do y'all think? Oh, wait.
It's not too bad. Is there any chance we can, I guess your computer's kind of screwed, but is there any chance we could get that file that you showed your Cal 2 students on the inverse of trig functions?
Yeah, I can send this to you. The problem is it's going to end and then it's going to start to have some stuff like as soon as you get to here, it's going to be like calculus stuff. So I can send it to you. I'll send it with the notes today if I can even recover the notes from today.
Yeah, no worries. I understand.
Okay. This doesn't look good. All right. So this idea, right? This idea of having an inverse for the sine function requires that we restrict the domain, and we all decided that we would restrict it between negative pi over 2 and pi over 2 for consistency of answers. Now, we have a name for this, okay? So there's two ways to write the inverse function. I'll just put them here. So there are two ways to write the inverse of the sine function. The first way is what I've been showing you. Y equals arc sine of x. That's one way you could write it, or sorry, sine inverse of x. And then the second way is to write it this way, y equals, and you put arc sine of x. These are just two different notations. If you write sine with a little -1, you're talking about the inverse of the sine function. If you write arc and then sin, that also means the inverse of sine. So if I go back and I ask you all the questions I just asked you, I could have done it this way instead. I could have said, hey, find arc sine of 1, right? Arc sine of 1 would be at what angle is your y coordinate 1? And you'd say that that's 90 degrees or pi over 2, right? I say, what's arc sine of 1/2? Then you would go in the unit circle, y coordinate of 1/2, this would be pi over 6. So it's just different notation, right? That's all that is just different notation. So when you hear me say arc sine, I'm talking about the inverse of sine. We good?
Is there a certain way you prefer
sir.
us to say it or write
I
it?
don't care. Me personally, I just almost exclusively use that notation. That's notation, but I'll say arc sine. You heard me say it a few times before. I didn't even told
Yeah.
you. I say arc sine, or I'll say inverse sine, but notation wise, they're equivalent. Those are the same things. Now, sometimes the arc sine is preferred only because students will make this mistake. Oh, look at that. It's not responding. What the hell is going on? Wow. This could become a really big problem for me. Yeah, I'm just gonna have to stop. Yeah, the -1 on an exponent, right? That normally when you have like x to the -1, it means 1 over x, doesn't it? Here with the -1 up there, it doesn't mean 1 over sine. And that's where people can get confused, because 1 over sine is just cosecant, right? And that's not the same thing as the inverse sine. So that's where people say this notation's bad. But you know, it's the notation. So all right, well, we didn't get through this. Definitely we got through the 6.2 inverse function. So that homework you should try. And okay, I'm back. That's weird, man. Okay. Something happens. All right, I think I'm going to end class, and I'm going to have, because I have another class today. I need to figure out what's going on with my computer before I have my Cal 3 class later. So let's call it a day. We still need to talk about the inverse of cosine, which will also have a domain restriction, right? Because cosine does the same thing. And then we have to do the inverse of tangent, inverse, and then all 6 trig functions have inverses. But all of them have domain restrictions also. So we have to sort through all that, and then we'll see how we can use all this. We'll start putting all this together to start actually doing like real world problems at some point. All right, everyone have a good one, okay? I'm gonna end class.
Wait, so
Okay.
real quick,
Yeah.
you wanted us to do the homework for 6.2 and 8.1?
No, don't do 8.1 because we haven't finished 8.1 yet.
Okay, because we okay.
Yeah,
And we'll
6.2 and then
do the-
chapter 7 stuff should be done also.
Okay, so the 7 stuff and 6.2.
Yes.
And then will the YouTube videos be up this weekend if we need help on a problem or anything like that?
For the homework,
Yes, sir.
yes, the plan is, but if my computer keeps doing this to me, I can't promise anything at this point. I've got to figure out what's going on. But my plan is to make the videos and post them for you. Okay. All right. If it gets worse, comes to worse, I might have just do handwritten and then scan them and just upload them as a file like I used to do back in the day. Just provide you the answers worked out without video. But we'll see.
I have a quick question as well.
Yep.
When you're taking like the square root of both sides,